Hello, welcome back to the Triple E 113 review. This part, we're going to run down the Adel processor, which was made by, I think, Sir Adel, to show you the different parts of a processor. Though this is a smaller scale processor, it's a good enough entry point for you to understand the different stages of a processor. Especially when you go to Triple E 153, where you talk about the RISC-V processor, which has more components and many more stages. Well, more components. So here, you can see that this is the instruction set, which is turned into machine code, which is turned into binary, which is read by the computer. Now, again, computers can only work with ones and zeros. That's why, we have machine readable code. And then we also have human readable code, which is the one that we see on our end. And then it's translated to machine code, then binary. And those bits enable certain operations for your processor. So, I guess important things to highlight are the clock. And that clock, actually, if you are into computer specs, you can see clock speed or frequency, which is usually in hertz. Yeah, that's how fast the clock can go on and off or trigger up and down. So 0101. Definitely faster than that. So the significance of the clock here, by the way, is every clock cycle, the instruction changes, or at least we shift depending. Because if you remember, we have sequential and combinational circuits. Sequential is those that need the clock, and then combinational is those that don't need the clock, which is your logic gates. So yeah, let's go through each part. So we have, again, the instruction set, which is assembly to machine code to binary, which is computer readable, machine readable. And this is the current instruction. So this is the hex code based on this translation. If you could see, you have 1010, which is A, and then 1101, which is D, and so on. So, it's a good practice. It's a good practice to know the binary and convert it right away to hex. So, the 15th bit is write enable, you can see here. And then the 14 and 13 bit is operation. And reg cell, destination reg, source 1, source 2, and a constant, which is discussed here. So, this is how the binary is actually turned into a machine code. And there are bit partitions, as you can see here, from bit 0 to bit 7. That space is dedicated for your constant or your source 2, or SRC2, sorry, yeah. And then from bits 8 to 9, that's for 1, 10 to 11, destination, 12, RS, and then 14, 13, and then 15. So that's the significance of this bit divider. And for example, if write enable is triggered and our destination register is selected as this output, then that goes to the register. And as you can see, there's a clock cycle here. So we have to wait for the next clock cycle in order for whatever enable we're having here. And then of course it goes to, depending on the instruction, it goes through the mux for data reads. And then here it's a register or constant selector, depending on, again, if the constant here is given and if the register select is also given. Because you can see, if you remember the mux, you have 2 inputs and then 1 output. So this is the selector. So if we select the constant to go out, then it has to be 0, which goes out here. And then if we select the mux to go out, then it has to be 1 for the register select. So slowly you can see the different components that we discuss coming together. So yung demux, and then yung mux, and then the select that we mentioned earlier, and then your machine code, clock, and so on. And then, that then goes to our operation, and it goes back to a register. So that's the rundown. Hopefully I didn't miss anything, but next we already talked about the machine code, and next we're going to be discussing problem 8.